In our previous modules, we have discussed linear models and we have also discussed several assumptions underlying the linear model. One of the assumptions was that the error variances are constant. Now, this is not the case in most of the real life examples. So, when the variances are not constant for the error terms, we say that the data set suffers from heteroscedasticity. In this module, we will learn about what heteroscedasticity is. We will know the consequences of heteroscedasticity, and we will also look at two different methods of fixing the problem. In this module, we will talk about heteroscedasticity and its consequences. Heteroscedasticity occurs when the error in our linear model has a non-constant variance. In such a case, we can think of the errors as each having been drawn from a different population distribution. And under that setup, the method other than the commonly used OLS to get the parameter estimate needs to be employed. When we learnt about linear models, we have also learnt about the assumptions that are underlying in a linear model. In some situation, there is departure from one such assumption or more than one assumption. One such instance is when the error variances are not equal, that is, when the assumption of homoscedasticity fails. So, let me walk you through the steps of writing the linear model and the assumption that we have just talked about. So, let us quickly recapitulate. One of the main assumptions of the linear model is homoscedasticity, which means if we have observations for I individual, the model can be written as yi equals beta naught plus beta 1 xi plus ei, and under homoscedasticity we assume that the variances of these errors ei's are equal. About the error term, we also assume that the expected value of these errors equals 0 for all observations I equals 1 to n. Now, heteroscedasticity is introduced when the assumption of homoscedasticity is violated. When homoscedasticity is not violated, the variance covariance matrix of the error term then looks somewhat like a diagonal element with all the diagonal elements equals sigma square, and we can also sometimes add a subscript of E to denote the variance of the errors. So, this is how a variance covariance matrix for the error terms will look like, a diagonal matrix with all the diagonal elements equal sigma E square. When homoscedasticity assumption is violated, we can then come across a heteroscedastic variance covariance matrix of the error terms, where the variance covariance matrix could take either one of these two forms. The diagonal elements are sigma E square times W1, sigma E square times W2 and sigma E square times Wn for I equals 1 to n error terms. Or it could look like sigma E square divided by W1, sigma E square divided by W2 to sigma E square divided by Wn. The presence of heteroscedasticity, however, in the data set motivates some pretty interesting concepts. Some of the concepts that we come across which are motivated by heteroscedasticity are as follows. It justifies the introduction of weighted least square estimators, and weighted least square estimator is just one step away from the use of generalized least square estimator of the parameters. The presence of heteroscedasticity also justifies the use of robust covariance estimators. When we have heteroscedasticity, in that case the error variances are not all same. When we want to estimate these variances, we can no longer use one common value of the mean square error. What we now can do is, we can use robust estimates for these variances and use them in prediction. Let me sketch some proofs and demonstrate the reasoning behind using robust estimators in the presence of heteroscedasticity. The first consequence of heteroscedasticity is that the estimates beta hat OLS, the ordinary least square estimates, are still unbiased and they are consistent. What do we mean by unbiased and consistent? By unbiased, we mean that the expected value of the ordinary least square estimates of the parameter beta is equals the actual value of the parameter beta. And by consistency, we mean that as we increase the sample size n to infinity, the estimate of the parameter approaches the actual value of the parameter. We will begin this proof by writing the expression of the OLS estimator of beta in terms of the sample observations xi and yi. Suppose we have a simple linear regression model written as yi equals beta naught plus beta 1 xi plus ei. In this case, the OLS estimate of the parameter beta 1 is given by beta 1 hat equals summation xi yi divided by summation xi square. We can now replace yi by bxi plus ei, where b is used as the coefficient of regression. Now, through a couple of simple algebraic steps, we arrive at beta 1 plus summation xi times error ei divided by summation xi square equals beta 1 hat. Now, applying expected value on both sides of this equation, we now have expectation beta 1 hat equals expectation beta 1 plus expectation summation xi ei divided by summation xi square. Now, one of the assumptions of our regression model is that the explanatory variable xi is uncorrelated with the error terms ei. Hence, the second expression on the right hand side, which is expectation xi ei equals 0, and hence we derive that expectation beta 1 hat equals beta 1. The second consequence of heteroscedasticity is that the OLS formula for the estimate of variance of beta 1 hat is no longer correct. Let the variance of the error term ei be denoted by variance of ei. Then the variance of the ordinary least square slope estimator variance of beta 1 hat is of the form variance of beta 1 hat equals variance of summation xi times ei divided by summation xi square, which now equals variance of summation xi ei divided by summation xi square whole square. This equals summation xi square times variance of ei divided by summation xi square whole square, because ei is the random term in this expression. Now, we assume that all the variance of ei's are equal under the ordinary least square setup when heteroscedasticity is not present. In that case, we put the mean square error as an estimate of the variance of ei, and thus the estimate of the variance of beta 1 hat equals MSE divided by summation xi square. Instead, we suppose that the true variance of the error terms are now s square plus si square, where s square is a common minimum variance and an additional individualized variance si square. Plugging this into the formula of variance of beta 1 hat, we now have summation xi square times s square plus si square divided by summation xi square whole square, and that equals s square divided by sum of xi square plus sum of xi times si square divided by summation xi square whole square. The first term here is roughly what OLS would calculate for the variance of beta 1 hat. The second term is the additional true variance in beta 1 hat that the ordinary least square formula for variance of beta 1 hat does not include. The third consequence of heteroscedasticity is that the estimate, the ordinary least square estimate of beta hat is now inefficient. When we say inefficient, what we really mean is that any estimator is inefficient when the variance of that estimator is larger than any other estimator of the parameter. We note that to prove an estimator is inefficient, it is necessary to provide an alternative estimator that has lower variance. Now, in order to find an alternative estimator, we now introduce the idea of using weighted least square estimator to obtain the estimates of the parameters. Now, let us look at the matrix view of this consequence. If we think of the prediction errors, which are yi minus yi hat as a vector, then we have a vector of order n by 1 written as y1 minus y1 hat, y2 minus y2 hat to yn minus yn hat. If we think of the sum of squares in OLS as product of yi minus yi hat prime and yi minus yi hat, then the sum of square of residual can be written as yi minus yi hat prime times yi minus yi hat. Weighted least squares can be now seen as the product of these two vectors with a matrix inserted in between, where the matrix is of the form 1 over variance of ei as the diagonal elements and 0 as all the off diagonal elements. WLS or weighted least square estimates always proceeds with the assumption that the off diagonal elements are 0. So, none of the errors are correlated with each other. However, when we proceed to the next step, which is the generalized least square estimates, that introduces the off diagonal components in the variance covariance matrix of the errors. GLS is mostly used in time series analysis. Now, here is an example where we will look at the plots of the regression line to see how the performance of weighted least square differs from that of ordinary least square. Suppose we have the variances of the errors proportional to the square of the explanatory variable, that is proportional to xi square. Suppose the true regression model that we have is in the form yi equals 3 plus 0.25 times xi plus ei, where ei is the error term, 0.25 is beta 1. Under homoscedastic assumption, standard deviation of ei equals sigma e, which equals 10. Under heteroscedastic setup, let us assume that the standard deviation of ei equals 0.05 times xi minus minimum of xi times sigma e. In that case, what we do is we draw 1000 samples from the population and we run the regression model, and we plot each of these regression lines. When we compare the regression lines of these 1000 fits under homoscedastic and heteroscedastic setup, we see that from the graph that in both cases the lines are centered at the regression line, the actual regression line, which is the true case. But in case of heteroscedasticity, they are more dispersed. On the next slide, we have the histograms of the 1000 slope estimates under both heteroscedastic and homoscedastic setup. Now, when we look at the two histograms, we can see that the distribution of slope under both homo and heteroscedastic setup is centered around the same value, but the dispersion is more for heteroscedastic setup, as we can see that the histogram is wider than the case where it is homoscedastic. So, the big picture here is that heteroscedasticity gives us estimates correct on average. The average value of the estimate of the slope remains the same under both homoscedastic and heteroscedastic setup. However, heteroscedasticity inflates the amount of uncertainty in the estimate, or it increases the variability of the estimates of the parameters. Now, let us look at the methods of fixing this problem. The first method is using a robust estimate of the variances of the parameters beta hat. Once the presence of heteroscedasticity is established, we would now like to look at means of fixing the problem. One such method could be the use of robust variance estimator for the unequal error variances and then deciding on the appropriate weights for finding the parameter estimates using a weighted least square method. We should not use ordinary least square method formula for finding the estimate of variance of beta hat anymore, because we know that there is heteroscedasticity present. Robust heteroscedastic consistent variance estimators are now preferable. Although we wish these were accurate for small samples, but generally the robust estimates are not. The best we can hope for the robust estimate of variance of beta hat is that they should be consistent and asymptotically valid t-tests can be performed. Now, let us recall the variance covariance matrix of the errors assumed under ordinary least square setup. We had a diagonal matrix where the diagonal elements were all sigma e square. Now, if we pull out sigma e square, we now have the variance of the errors as sigma e square times an identity matrix I. Now, if there is heteroscedasticity, we have a variance covariance matrix of the error term which is of somewhat this structure. It is a diagonal matrix with the diagonal elements sigma 1 square, sigma 2 square, sigma n square for E1, E2 and En the error terms, and all the off diagonal elements are 0. Now, in order to find the estimates of the variances, we need to now estimate these n variance terms, which means estimate of the variance of E would mean finding estimates of sigma 1 square, sigma 2 square and sigma n square. In order to obtain the robust estimator of variance of beta hat, in turn, we will now need to find the estimates of the variances. What we do in order to calculate the robust estimate of variance of beta hat is that we know the true variance of the OLS estimator is variance of beta 1 hat given by summation xi square times variance of ei divided by summation xi square whole square. Assuming homoscedasticity, we estimate sigma e square with MSE. So, variance of beta 1 hat now equals MSE divided by summation xi square, and the square root of this expression will give us the standard error of beta 1 hat. But according to White, the robust versions of finding variance of beta 1 hat is to replace variance of ei in the above expression with other estimate. White suggested using ei hat square in place of variance of ei, where ei hat square is the square of the estimate of error that we obtain after fitting an ordinary least square equation to the data set. Using the weighted least square method of obtaining the estimate of the parameter is efficient. It is more efficient than the ordinary least square estimates of the parameters. What this means is that the WLS estimates of the parameter has a lower variance than the ordinary least square methods. However, WLS is more difficult to estimate. Because we have more terms now incorporated in our model, we have a difficult expression to solve for finding the estimates of the parameters. In WLS, we are required to find the estimates of the parameters by minimizing the sum of square, which is in the form summation I equals 1 to n wi times yi minus yi hat whole square, and the weights here depend on standard deviation of the error term. So, we need a model for the variance of error term sigma I square. Another method that can be used is data from categorical groups can be combined together. Suppose we separately investigate data for men and women. For men, the regression equation is yi equals beta naught plus beta 1 xi plus ei, where ei is the error term. In case of women, it is yi equals C naught plus C1 xi plus ui. Then we can wonder, can I combine the data for men and women to estimate one model? In that case, the model would look somewhat like this: yi equals beta naught plus beta 1 xi plus beta 2 sex plus beta 3 sex plus xi plus ei, where sex is a dichotomous variable which takes the value 1 if it is male and 0 if it is female. But in this model we have assumed that variance of ei equals the variance of ui. We should have tested for homoscedasticity, because if there is no homoscedasticity, we cannot pool the variances in the cases. A second method that we can use is by simple random coefficient model. We start with the regression model that has a different slope for each case, where the model looks like yi equals beta naught plus beta 1 xi plus ei. The slope here is considered a random coefficient with two parts, where beta I equals b1 plus ui. b1 is the same for all the cases and ui is the noise in the slope that is individually assigned. The regression model then becomes yi equals beta naught plus beta 1 plus ui times xi plus ei. Note that the new error term in this model is not homoscedastic. What would be the variance of that? We apply the usual rule of variance and we obtain variance of ui xi plus ei equals xi square times variance of ui plus variance of ei plus 2xi times covariance of ui and ei. We get rid of the last part by asserting that the two random effects are uncorrelated. So here we have seen that we can get rid of heteroscedasticity, or rather we can take care of heteroscedasticity by obtaining weighted least square method estimates for the parameters, or we can use several transformation of our regular linear model so that heteroscedasticity can be taken care of. In this module, we have learned what heteroscedasticity is. We have seen some serious consequences and we have learned how to get rid of heteroscedasticity from a data set. In the process, we have learned different terminologies in context of linear models and the estimation of parameters of a linear model. For instance, we have learned what ordinary least squares are, and we have also learned what weighted least squares are and how we can use weighted least square in order to fix the problem of heteroscedasticity in a data set. Now, there are several tests which we use to detect heteroscedasticity in a data set, and we will dedicate a separate module which will be a follow up of this, and we will see you then.